In order to start label image, you have your label image command, the path to the folder where you have your images, and if you have a predefined classes files, but in our case we don't use that. And you just execute the command and you will get this display. So here on the left side you have two folders. You have the open dir, where you can navigate to the folder of the images that you want to label, in our case is correct, and the save dir. The save dir is actually the label dir. So if we are going to select the labels, train, okay. Now you see, as I mentioned, I already had some label data, so you see the labels that I have labeled before. So what you are going to do for the label, let me show you the shortcuts before. So if you look at your keyboard, you'll see the A keyboard from the left side. That's going to be the shortcut for navigating to the previous image. D for navigating to the next. S you use to save the image. And to activate the rectangle box, you're going to use W. Let's see say that I don't have this data here. I want to delete it. You can work with your mouse or with the command. I'll delete it so that you'll see what I'm doing. So make sure here you have YOLO activated. If you click, you have different options, Pascal, YOLO, but we have YOLO. And we have this create a rect box. This is the part that you click to create a rectangle. You create a rectangle around the object that you want to identify, regardless of the object orientation. So if your object is tilted, you just select the area containing the object, like this. I pick and you specify the name of the class here. I've selected this image to show you that in reality we have obfuscated objects. What you should do in this case, you should select the object as you consider to be available. So we'll select for the red card here this object. And you'll see that it's already written card. It didn't know to detect it, but it uses the classes that you've selected before. So if I'm going to add a new class name here, you'll see a list of all the classes that you have. And then you create this rectangle here. Card. You save the image, because otherwise it will not save it for you, and you go to the next image. Here again is saved, or you can use your shortcut keys, A to navigate previously, D to navigate to the next one, back, and W activates this rectangle. So if I'm going to display this rectangle with W, just activate. You don't have to go with your mouse here. When you are going to have to label thousands or tens of thousands of data, this is going to be useful. So it depends. In some cases you'll do it, in some cases different teams will do it, but in either way someone has to do it. So we have the different objects here. We have objects that are going one around the other. Maybe this one is better to capture. Try to go as close as possible to your object. You don't have to be pixel perfect, so I don't really have to be like here or exactly on the edge. I can be a little bit higher. You don't have to be pixel perfect, but if you are going to select a lot of the data, you may get to the point where your models understands that part of the background data that you've included when selecting the object is something meaningful, and it's going to do that to do the predictions. You go through the objects. If it's a full image, like here, you select the bounding box to be as large as the whole image. Like I have here different example of different cards that I've found on using Creative Commons. They all have the same number, 8888. It's easy. Not all of our examples, just a batch. So you have whole images, you have extra large images. As you can see, it's not necessarily the full image, but it's almost close. And then this is how you should label it. Let's see several examples. As I mentioned, if it's tilted, you have to draw a bigger bounding box to cover the object. You may choose not to include part of the objects. I've included this example. I've chosen not to include the other cards. They may be cards, but actually they may be business cards or something else. So if you are not 100% sure what an object is, it's better just not label it. Just leave it like there and discard it. You have enough examples for the correct ones. So you can work with, delete it so that I'll do it again. Just as I mentioned before, you can work with the mouse and you use this create rect box. And then choose the label. I've chosen car because this is what I've done before. This is the model that we have. And then save the image, Command S or Control S. And go to the next one. So this is basically how you label. I hope you got an idea. If you have questions on this part, or how should you treat different cases, I'll show some example. Yeah, you can see I've also labeled some data as well. But I'm not going to go in that direction because it's my real card. You don't have my card in the images. Okay. So I did include something, as I mentioned. I've included some resources to be able to just try to create a model. It's a limited set of images, so in order to achieve good results, you'd have to have more images than this. I haven't included my card in there. So as I mentioned, you have this resources train images folder. And YOLO is working with images and labels. So you have the images folders and the labels folders. And I included them here. You can take them, and then you can upload them in your Google Drive at any location that you want. If you're going to do this, you'll be later to generate a model using these classes, these resources, sorry. So for the images, I have the train and val folder, and for the labels, the train and validation folders. What I have here, little bit of what's on label. Let me just make it smaller so that you can see. Do you see my screen here? The image. I don't know how to get rid of the right part. So for each bounding box that you create, you'll have a txt file looking like this. So you'll have a txt file. Let me make it larger so you can see. Of this assumption, with each bounding box that you included on an image. So for each image, you'll have a txt file, and for each txt file, you'll have all the different bounding boxes that you've added on the files. And what are these numbers? This is the class number, but maybe you'll see it better like this. So you have this annotation file looking like this. This Zidane picture is included in YOLO v7. So it's a reference picture. Let me just exit. And you have this 0, 0. This is a little bit different than the regular coordinates axis. So the coordinates is top left corner. That's the 0, the origin. And you go from top left to bottom right. That's 1, 1. Everything is between. It's a floating number between 0 and 1. And you have these annotations looking like this. And what you have the class. That's the index. As I mentioned before, you are working with index of the class. So if you have 5 classes, you will have 0, 1, 2, 3, 4 as the index of the class. But don't worry, later on you can work with the names. It's just how it's stored. And then you have this x center, y center, the width of and the height of the image, or of the rectangle, sorry. So you have the xy, that's the centroid, the center of the bounding box that you've created, the width of and the height in relation to the image that you have. And you have labels like this. So if you take the resources folder here, and then you just upload them in your Google Drive, wherever you want, you'll be able to later on generate a model based on that. In order to train the model, as I mentioned, you need to define the train, the validation set, and different from other models, for YOLO, you don't need the test set, but it's highly recommended, of course. But you need the train and the validation because without them, you're not going to be able to generate. And then you define a YAML file. Each model starts with a YAML file. And in this YAML file, you must have several paths to the train, the val, and if you have the test folder. This is relative to the location where you are. So you'll see in my Google Drive, I have here YOLO v7. This is the path. You'll have the same YOLO v7. So I created here the train folder where I put the images and the label that I copied. So you can choose whatever path you want. Just make sure that you point to the correct location here. I haven't spoken about splitting the train and validation. This depends on how much data you have. So if you don't have a lot of data, you're going to use quite a lot of the data for the train, and then you'll figure out later on different means to generate that data. The validation will be useful to understand the model. When we look at the metrics that you'll have precision, recall, mean error precision, but we'll go into that further on. But it depends on the accuracy of the model that you are aiming, what you want for the model not to learn. It may get to adding more data, For example, one model can learn like the rounded edges of the cards, and everything with rounded edges can be detected as a card. So you'll have to have examples to show them this is not a card. So you have to add the data for that particular example. And you have to have the different angles or the different clarity of the images, brightness, and all kinds of examples. So that affects how many examples. I've just included a few, I think it's 70 something, to be able to just generate the model. But if you want to build your own, you can gather the data, label it, or if you have already labeled data, because there are data sets with labeled data on hand, and then you'll have to define this YAML file. So going back to this, we'll have the train, the validation folders. This is relative to the folder where we are, because in our collab, I've changed that directory here. So this is where I'm starting everything from, in YOLO v7. Number of classes. You can define a model to detect several classes in the same model. Depending on the complexity of the model, you may decide to have more classes into one model, or different models, different smaller models that are tailored to one specific class. One example, we had detection for the different phones, and as I mentioned, we wanted to detect the phones, but we are using this detection to detect in a flow where the person is inside the phone. So we had problems because we have the person, which is a known class, inside the phone. So when the model saw a person, it tried to predict the phone. So in order not to do this, you just label the phone as a different class, and then the person as a separate class. Or you hide the face, and then you select the margin, or you do segmentation for the margin, as you may see fit. So as I mentioned, you may have one class or several classes, so you have to put the number of classes here. And then the class names, because it's going to be easier later to track what your model is doing. So you'll have to define this YAML file, and then you'll have to add this YAML file to your Google Drive where you are working. In the research here, not here, sorry. Not here. I've also included a YAML file here. In the card detector config, this card.yaml that you can get directly, and then you can add that to your Google Drive. Or you can create your own. Okay. When you run your model several times, it will try to build a cache, so that's why I've included these lines, because I've already run it. And if you change your data, sometimes it tries to get it from the cache if it's on the same location, so that's why sometimes it's a good idea to delete your cache. And in order to start training, that's really easy. You can use the built-in trend.py included in YOLO v7. You see here. Yes. It doesn't matter. You put it later on when you run it. Wherever you find it easy. You have this train.py included in YOLO v7 module. And we are going to use that. And then we'll go through the different parameters that we need. Not too much. With this exclamation mark, Python 3, this is how you can execute directly a Python 3 command from your collab. So we have .train.py, and then we have to specify the image size. I've kept the 640 image size. A configuration of a YAML for the base that you are using. So if you are going to look here, where was it? In config training. You have several built-in YAMLs, so for the ones that you can start from. So you need both. You have your YAML, which is pointing to your data, and this is the base model that you're starting from, so you need the YAML for that one. And if you're looking at this YAML, this has more, so you still have the number of classes, but you also have the YOLO Vixable backbone. So basically, the backbone of the model is between this YAML file, so that's pretty important. And then you have some hyperparameters. YOLO comes with some hyperparameter configuration files that you'll find in data folder. You'll select the one that you desire. Custom MP5 had quite some good results. You can try, and if you see, not a lot of the there are not a lot of the differences here. It's most how you do here mosaic and the different operations that you do on the image. The learning rate, the initial learning rate, and you'll see here this one, what I mentioned, the mosaic and the mix-up. Is the mosaic, what it is, it basically during training, if you, by default it's running with mosaic. If you want to avoid mosaic, you can use rect, so just use plain rectangles, no mosaic. What mosaic does, it does a mosaic of your data. So it basically regenerates different images with the bounding boxes that you have on different areas, because in reality, a card can be on the lower left corner and in the upper right corner, so it's the same card. It doesn't matter the position in the image. So that's what the mosaic does. So we'll see some example with where it's running, and you can have a look at what's behind with a few examples on the trainer. So I'm letting this mosaic on for P5. The batch size. You can play with this, and it depends on how much memory you have. If you have problems running with a larger batch size, you can just run with smaller batch sizes, and then it will still have good results. And the epochs, I've chosen 40 because in my example, I've tried several examples, and actually I started with way more, and then I saw that it starts to overfit, so then I lowered this. And the data, that's the YAML that you created, point to where is your data. The weights of the base model, because we mentioned that we are starting with this base model. You can build from scratch, but that's going to take longer. Use all the workers. Use the first GPU available and the name of the model. And these are the parameters that you need to be able to train the model. When you start them, I'm going to start the model. I'm not going to wait because I already have a model. And I've also included a model in the resources that you can play with. It's a very basic model built with like 100 models, but even so, you still have some good results in some examples. So you can see that it's starting. It starts to scan the data that you have. I have 132 images in my folder. It starts with the train, with the validation, and then you see it starting, and then you see the metrics progressing as you run the model. You'll see the class, the total, and the labels that we have, the image size, and then you'll see later on the precision, recall, and the MAP. And then we'll get to that. So as the model is progressing, I'm waiting for one epoch to end. You see the progress here. Depending on whether you run it on GPU or a CPU, it will take different. If you have premium Colab account, then you'll be able to use GPU. If you have the free option, you can use GPU, but that depends on the availability. So I've had cases where I couldn't use GPU on the free version, or I could. Depends how much is available at that time. So we have here the first epoch done, and then it's the second epoch, and then we have this here. We have P for precision, R for recall, and this MAP for 0.5, and in MAP for 0.95. And we are going to talk about that later. So the precision is recall is like the precision and recall for any machine learning problem that you have. It's the same notion of precision and recall, and then we'll look for the others. So how many of you know what's precision and recall? Okay. So then we'll dig into that. So P stands for precision. How precise am I when I'm saying something? So if I have all the positive precisions, meaning that all the cards available in my training set, if I say that this object is real, that's a card, am I true or not? So it's all the positive precisions, what proportions are actually positive? When I say positive, I mean the fact that I got the correct answer. That's right. So if I'm looking for a dog, I have a dog in my example. Or you can think of how accurate am I to say something right. So if I say it's a dog, I'm 45% probability to say that that dog is real a dog. That's precision. Now recall. Recall looks of all the data. Did I capture it all or not? Maybe I capture, so I have 100 dogs, but I've correctly predicted 30 dogs. That's a precision, that's a recall of 0.3. So of all the total cases, of the positive cases, of all the total cases that I have, what proportion did the model capture? So that's recall. How much of the class did that model actually manage to predict? That's recall. And then we'll go later on. If you see here, we have P for precision, R for recall, and we have this medium AP, medium AP for 0.5 and 0.95. And what we have this for MAP, that's average precision. We need to talk about the intersection of a unit first in case of the object detection, because if I have another example, I have a classifier that if I predict from a classifier that's a dog or not, that's 1 or 0, it's true or not. But in the object detection, if I get part of the image right, am I right or am I wrong? So that's why we're going to talk about intersection of a union. So let's say that we have this example, and I have this card. The green box is the ground to box. This is the correct label. My model predicts the red one. That's the prediction box, because you will not always have exact labels. So that's why in case of the object detection, you need to understand the intersection of a unit. How much is the overlap of your prediction to the actual prediction? So this is the prediction, this is the ground truth. And if you overlay them, this is something that you'll have. So it's exactly the same image. So you'll have this part, you'll have this part for the green one, and this, the center, that's the intersection. It's both parts. And everything, that's the union of the two. So when you say that a class is either true or not, so it's that class or not, you take it into consideration or you not, you have to specify that intersection of a union, what I've shown you before. Yes, you have a question? Oh, okay. No. Exactly. I'm not sure why. Maybe you can see better like this. So we talk about this intersection over unit, and I've mentioned that you define that intersection over unit when you, in your options. I've showed you the options where we've defined it intersection over unit. That's how much you accept to be overlapping in order to say that it's true. So if I say 50%, that means of all the overlapping part, that it's 15% of everything that's, what's the union of the two bounding boxes. And then we get back to precision of recall. So we have this intersection of a unit, and you have this threshold, how much you accept as an overlap to order to say yes or no. And then you say you have your precision or recall depending on this threshold that you set. And then we have this mean average precision. But first was the average precision. That's actually the area under the curve. So if we plot this, let me make it smaller. So if we plot this recall on the x-axis and precision on the y-axis, and you plot the curve, so at any given confidence point, what's the recall and what's the precision, then you'll get this sort of a graph. So of course, if you have to be really, really confident that you're right, then you have a high confidence threshold. Your precision is high because precision means when I say something that's real, so your precision is high. But if I'm really, really confident that's something true and I really need this high confidence, then my recall is going to be low because I'm not going to capture all the data that's available. So finding that sweet spot, it's a tricky question. Of course, the optimal one is here, is this corner. So full great precision, one recall. If you have something like this, try to have a second loop because you may lose something. You can reach like very, very, very good results, but 1-1 for all the cases, really tricky. So you have this area under the curve. So in order to compute it, so you can consider it like building into smaller chunks where you can have like rectangles, and then you can compute the rectangles for this, to be able to compute this area under the curve. So you compute the area of the curve. So as I've mentioned, you want your model to be here, as close as possible to this corner. So if the area under the curve is high, then your model is good. If your area under the curve is low, your model is not so great. So you can have one precision 100% and recall 10% because you just favor one class. You just say everything's a dog. Of course, you'll find other dogs, but when you say that it's a dog, that's not really a dog, it's something else. So we need this area under the curves, and you have this area under the curve metrics for the different machine learning objects, and in particular for the object detections, you use this and you name it as average precision. It's basically the area under the curve that you have under the precision recall curve. And the mean average precision is the average of the average precisions across all the different classes that you have. If I have 3 classes, and for one I have an average precision of 10, and for another one, not 10, sorry, 0.1, 10%, and another one is 0.15, and another one is 2, the mean average precision is going to be 0.15, the average of all the 3 for the different classes. In our example with the card, we'll have one class, the average precision is going to be the mean average precision. So this is one very important metric that you have to look at. And you'll see here that we have 2. We have the 0.5 and the 0.95. And this relates to that configuration that I mentioned, the intersection over union that you mentioned. How much should it be, and what's your confidence? And you want to make sure that as your epochs run, the model is progressing and is increasing. You've seen here the details, and now to test the card detection that we've generated. As I mentioned, I've already included one card detector. Here. In the resources. No. Yes, yeah, it is somewhere. I think I didn't put it. I'll put it in the GitHub account, but we can have a look. It's just one model that we have, and this is how you are using it to predict the daytime. So we have the option that we mentioned before. So we have the weights, that's the path to the model. I've already included this card.pt file. The image size, the confidence threshold, so you don't go below this confidence. The intersection of a union, so meaning you need a 45% overlap in order to say something that's real. My device is the first GPU. I'm not filtering anything. And I have an example to test it. So in YOLO v7 inferences, images. I'm clicking. Okay, I have this download.jpg. So I have this card that I want to predict on. So if I'm running this model that's reading the image, just as we did before, loading the model, same method. So even if it's custom model, it's the same method to load it. And the same predict on image function that we've seen below with the football players. So we have something like this. Let me make it bigger so that you can see. So my model detected that in this image we have a card with a 0.72% confidence that it's real. I can also test it on a video. I have low battery. I'll get my charger. 1 second. Okay. And now to predict on a video, what we are going to do is going to do the same step as gathering the data frames for the video, just that we're going to use the same video capture using the properties because we are going to write on the video. We're going to write on an output. This is, we create a new video with our frames and our prediction on top of them. And iterating to the frames, we're going to do a prediction on the video, same function as above. And also, I'm writing on the same frame, and I'm outputted in this output. That's a video writer where you can generate a video of your output. And then I'm closing it. And if I run it, I run it. This is the definition of the method, and if we run it, you just specify the video path, and then you call this method predict on video. If you look here, I wanted to print out how many frames are processed. So if you can see, it's processing quite fast. And you can also have a look on the real video. This is the path of the video that I've generated above. I'm compressing it to be able to display it here in Colab. So if you run it locally, you don't have to do it. And I'm including this HTML sort of thingy. That's showing the video that I've put here. So the video is something like this. As you see, whenever I move the hand, my predictions are following the detection. So if I tilt it, the boundary box, it gets bigger. And you can see it can follow without any problem the card. Even if I had only 130 files for the train data, I still was able to generate a model that is able to follow the card. You can also run it real time, like on the webcam. And you need some utility classes for these ones. This is actually, so you do have to do it like this because it's Colab, but you find also here in the project these utils. You have the stream.py, that's the way faster and easier option to do real live streaming. So you just have this video capture, reading the frames, process whatever you want on the frame, and then show the frame, and that's it. But in Colab, you need to have this base64 image display and the JavaScript behind. You do have some hints from Colab to do this. I think here, not here, codes, one of these, yes, this one. You have this camera capture and you have the basic JavaScript that you need to tune, to edit. So once you have that, this JavaScript, and we have these, the different conversion methods from pil and the stream, JavaScript stream. As you can see, it's building actually a div where it's displaying the video. And I have this method. This is the Python that I'm using, predict on stream. So just as before, I'm reading a frame one by one. I'm processing it, and I'm predicting on the image using this bounding box array to display it later on. So if you have a look, I'm using this bounded box array to write as on the output, and then this is how I'm doing it. So if I'm running it, I haven't run it. So this one, it should actually start my webcam. Let me make it smaller so they can see my screen. I think you can see my screen. So this is the webcam. It has a bit of delay, and even for prediction because I'm working with the server. But if I'm putting here the card, it has a bit of delay for displaying it, but you can see that it's following the card. If I move it in the different areas, you see the different detections that I have. Running it on the local computer will be way faster, so you can do this as well. So if you saw, we can build our model, train it, and then put it to work on an image, on a video, on a webcam stream, whatever you see fit. Thank you. If you have any question. A lot of information, I'm sure, for 2 hours comprised, but it was the fast-forward track on object detection. Yeah. Yes, YOLO v7 has a separate branch. It's called the mask. If you have a look for the mask branch, it's actually using the masking, like for the segmentation. But you can with that mask branch. What are? Yes, RCNN. You have this, but actually you can. We wanted to do an object segmentation, for the ID cards, but it actually didn't make sense because you spend more time to gather the exact contours. So we built our own models, our own stacks, but it was way too painful to develop it. So then we just scrapped it, and then we just used object detection. If you have other questions?
What's the real application of such a model? I mean, obviously it's fun to identify parts in the webcam, but how would you really use it for your bank?
Yes, so what we have in our production working, we have a part, we have the user identification model, what we call it. And that part has two options. First, the user is required to show his ID card to the camera, and we have to extract the crop of the ID card from the image, the face, and the data on the ID card. But in order to get to the crop of the ID card, because we want to save in our system just the ID card, not the image with everything that's behind, we need that crop, and then we have an object detection to detect the ID card, and then we shift it to 0 degrees, and then we have a second object detection to have the correct crop of the ID card. That's one thing. The second thing that we are using object detection is what I mentioned before for detecting devices. Because in the next step, the user is required to start his camera and to do several actions that we ask him to. Look left, right, and we check different things. We check that the user is looking in the direction that he wants. You can still use YOLO for pose estimation, but there are other simple options for this. Maybe you can chat later on. And we also have this device detection part, where we use object detection to detect the presence of a device. So if we see that the person is actually showing a phone with a person inside that phone, that means that that user is not real, that he wants to fraud the system. So then we just disregard the entire video and we mark it as fraudulent. We do have cases where where it's trying to identify themselves, sorry, they show a phone with another person, with a video of another person inside that, or an iPad, or a video from a conference or something. So whenever we detect the presence of a phone, tablets, TVs, or other objects containing the person that we want to check, then we mark that as fraudulent as well.
But if you get close enough?
Yeah, so if it's that close enough, then it goes on to the liveness detection model. We do have a liveness detection model, but we check several frames to make sure that it's okay, and then it takes longer to predict. But if we find this detection in the first frame that we want to process, then we just disregard the full video and we don't do the liveness detection, which is more intensive. If you have other questions? I'm happy to help you. I'm also aware that it's a lot to do in 2 hours, but I wanted to give you all the tools that you need to be able to do your own modules. So you have everything in the repo. You have the utility classes as well here. So you are able to do whatever. You have the image set generation from frame here if you want to do it locally. And you can use this to kickstart your own model. Thank you. I'm happy to share more in the breaks.